All right, good afternoon. Can everyone hear me? Excellent. All right, so my very vague and mysterious title, the observer effect in cyber Feng Shui, I'll be talking about today. Before we get started, or before people wander out, I wanted to talk basically in a nutshell what my talk is. So if you guys fall asleep or wander out to the coffee machines out there, at least you'll try to remember this. So basically what this talk is about is using existing hardware or misusing existing hardware in a non-traditional way to be able to build a trusted botnet or a trusted implant network where on an offensive operation you can detect if someone is trying to virtualize you or debug you, to be able to create device-specific keying material so that you can't be viewed or decrypted on another system, and then lastly to run in an encrypted mode so it makes it very difficult to be reverse engineered. So this is a technical talk, but you're all pretty technical. It does cover a lot of topics. This is kind of 3 topics crammed into one. I will be moving fairly quickly, but if you have any questions about clarifying of acronyms or terms or concepts, please raise your hand at any time, because most likely there are 5 other people that are just too shy to ask the same question, or I did a really bad job explaining something. So I'd rather have you know as soon as possible. I gave a talk at a conference in Las Vegas, and I asked any questions. I told them the same thing, no questions at the end, no questions. I said, all right, well, see you at the bar. And everyone got up in line and asked the same clarifying question one after another that they were too embarrassed about. So please, if you have a question, raise your hand. More broad or typical questions, please hold to the end. So really quickly, who am I? I live in Denver, Colorado, where it's always sunny and not humid, unlike here. I lead the low levels computer architecture group, so that means mostly I play in system management mode, I write hypervisors, or I write my own BIOS. I'm one of Sergey Brodis's Langsec co-conspirators, and I like ultra running or mountaineering, etc. So we're going to talk about why this is a problem and introduce kind of what we're going to talk about. The Triforce, those of you who are Zelda fans, so there's 3 pieces to this. There's the software dynamic root of trust, which allows you to make sure that you're not being run in a virtualized environment, or make sure that there's not introspective hypervisor or debugger, which builds off of trusted computing. We're going to talk about device-specific keys, so that's using the physically unclonable functions, as they're called, or puffs, and then talk about some crypto on top of that that provides some extra capabilities. And then the last one is a secure execution enclave, which helps defend against reverse engineering, and that's encrypted execution. And we'll put it all together and then draw us a couple of conclusions. So on a red team, so I'm going to be talking as if I'm a red team and I'm legally doing all of this stuff. And so when I say it's bad or it's hard, it means that the defenders are doing a good job. But you can also assume that this would be something that you might want to defend against in the future. So after you've got in and got a foothold in the network, next generation AVs, introspective hypervisors like we saw in the last talk using libvmi or JACVUF or some of the other tools, FireEye has a hypervisor. Basically, they are now able to try to infer more and more about what your application is doing, and they're trying to flag it as soon as possible. And so also what happens is you'll have a reputation-based file system, or AV, where once it finds an odd file on your corporate network, if it's nowhere else, it might actually ship that file off somewhere else for someone to do some analysis on. And so as if you're trying to be really persistent on a network, you want to make sure that you're not giving up your tactics, techniques, and procedures, or TTPs, as long as possible, because you want to maintain presence on there. You also want to make sure that you're not burning your capabilities or giving them too much information about what your capabilities are. And so that's very important, especially if you're dealing with a very high-level red team where you're using a fairly expensive, say, zero-day or a new type of attack. You don't want to give that up and make that public in case someone catches it. So there are 3 tools, basically, we're going to bootstrap. So the first one, when you get on your kind of initial stage 1 dropped binary that you have execution control, you want to figure out whether or not there's something on there that's trying to see what you're doing. And so that could be, am I running on FireEye? Am I running in a debugger? Or am I running on the system I think I'm running on? So this is the observer effect, basically, which most people conflate with the Heisenberg uncertainty theorem, where you think which the action of observing changes the result. And so basically the presence of introspection and introspective software running on a system will in fact change the behavior of that system, and you can try to find that, and that's what we'll talk about. Number two, so we're going to generate device-specific keys that allow you to tie cryptography to a certain host or certain device. That's kind of getting cozy. Once we're in and we're feeling comfortable that no one's kind of prying into what we're doing, we can kind of work on the Feng Shui of the hardware and kind of get a little more comfortable. And then the last one is the opaque execution environment. And this I'm going to go over very quickly. This is the talk I gave a couple times last year called HARES, Hardened Anti-Reverse Engineering. Basically a capability to run a program encrypted at near native speed on COTS hardware. So that I'm going to skip over very quickly, but at least just provide you a place to go look for more information. So let's get going right here. So first, a little bit of background for introspection. So trusted computing. On the defense side, it's basically a field of security that tries to establish a root of trust, which is something either hardware-backed or software-backed, that then you go from there. And so you're trying to make sure that you know what's running on a system, and only that can run on a system, or at least you know if something is gone awry. And you kind of extend that, what's called a chain of trust or a trust chain. You'll think the trusted computing group is kind of the main force behind this, which is kind of a coalition, and you see Microsoft and their Palladium effort was similar to that, and then they kind of provided the TPM, and now they have other extensions on top of that. For a defensive operation, if you actually deployed this, it would be pretty popular and very helpful because you could look for kernel rootkits pretty early on in the game. And it's actually becoming much more popular. So Windows, I think as of 8 now, it uses UEFI secure boot. And so if you try to load an unsigned or legitimate driver, it'll actually prevent that from happening, and so you'll know whether or not your kernel is safe. And also TPMs are very, very common on x86 platforms. Most computers come with them. So this gives you the ability that you can kind of ensure that only signed or known good bootloaders can execute, and then you can follow that path all the way up. Another feature that's provided by trusted computing that's less commonly used is called remote attestation, which is basically proving to a remote entity in a very strong way that you are in a trusted state. So saying, yes, I am running the DRM client that you want me to, or yes, I have not been hacked. So there's different measurement types. So static and dynamic, and then hardware and software based for each type. So static measurement, basically you start with some boot ROM that's hopefully not rewritable on the CPU or in the initial ROM on the motherboard, and then you kind of measure every step thereafter. The problem with this is that if you have some legacy software you need to run that doesn't measure the next piece, so this was common with PCI option ROMs, you'll get into the issue where the chain of trust kind of gets broken. And so that's kind of the downside with static measurement, but that's basically UEFI secure boot. To combat these concerns, Intel's trusted execution technology, TXT, provides dynamic measurement, where basically you can run and you can boot up an entirely hosed system and then basically click a button, so to speak, and then reset the CPU into a trusted state, and then be able to attest that you've done that successfully. And so that's what the T-boot tool does for Linux or for Zen. That chain of trust, so TPMs are a hardware-based tool. They have registers, platform configuration registers, PCRs, and they really only have two things. You can either erase them back to their initial value, or you can extend them. So you can't really write directly to them because that would kind of break the purpose if you could just set them to arbitrary values. They're extended basically by SHA-1ing the old value of the PCR and the hash of the new software you're measuring. And that means that you'll hash at the end, as long as every piece of that chain was the same, should be the same from every time, and you can detect a single link in that chain being broken. And obviously, unless you can reverse SHA-1, you can't set it to arbitrary values. Remote attestation typically uses the TPM. They have a key burned into it that's signed by the manufacturing, the AIK, which is non-exportable. And basically, you can use that to sign those values in what's called a quote and provide that to someone else. You can basically show that you've loaded up in a certain condition and everything is looking good to a remote entity. So our goal is to make sure that there's no other process, whatever, regardless of what privilege level it's running at, is trying to basically cross that isolation boundary to introspect on what we're doing. So the x86 platform has done a very good job of trying to trick developers into thinking they're running in their own little world. They have virtual memory. They have all kind of handled in hardware operating system multitasking, so you don't have to worry about that. So you kind of have this development mindset that you're pretty much running only on the computer and there's nothing else outside of you. But that's clearly not the case with virtual machine introspection, for example. And then once you find introspection, or if you find introspection, maybe you'll change your TTPs for that system. You might try to quickly pivot somewhere else in the network just to get off of that system. You might like delete yourself or try to do a lot of weird things to make the forensics analyst's job much harder if you're doing a lot of random stuff just to make their day more complicated. And then also you don't want to drop anything else on there because you might lose more capabilities. And so there's different responses, and that's kind of depending on your operation you're running, but it's really helpful to know if someone is running or if you're running on a honeypot. So out there in the open, this is something I've not done. This is just a tool out there, but it's just kind of a good start. Paranoid Fish, it's a tool you can get on GitHub. It's open source, and basically it uses all the techniques that open malware samples have used to try to figure out if there's a debugger. And so this is a really great tool if you're an AV vendor to figure out, okay, am I going to be flagged by this? Or if you're a malware author, you want to make sure that you're hitting all of these because this is kind of open knowledge by now. And so this is just a screenshot. You'll see it's checking. I mean, some of these are pretty comical, like is debugger present, etc. And if your AV is returning, yes, there's a debugger present, it's probably not the greatest. So this is a great resource, but we want to talk a little bit further down about how to misuse the architectural features. So CPUs have worked very, very hard, and Intel and AMD and all the chip manufacturers have worked very hard to provide this illusion of isolation. So back in the DOS days, if an application was misbehaving, it could just overwrite the kernel and crash the system. Now you have CPU-assisted virtual memory. You have that also for hypervisors to multiplex between operating systems. You have really nice multitasking, so an application doesn't necessarily even know when and when it's not being scheduled to run. However, many of these are shared resources. And when you have a shared resource, there is some form of side channel there that allows you to determine a little bit of information about is there something else running, what is it doing maybe, or how much load is it consuming. There are two specific talks, the closing keynote by Sophia, and then tomorrow Anders is talking on a very specific CPU cache side channel. So if you want the really nitty-gritty details, I'd recommend go with them. Go to those talks. So again, shared resources, you have the CPU cache, the CPU pipeline, timing and load information, and all of these right here are kind of hard to completely emulate and isolate. And so if you can measure them and how they're changed, you can infer other behavior. And then you can see what other processes may be doing. So we worked on a program called Cache Teller that basically used the shared cache in a multi-core system to be able to figure out the pattern of instruction accesses of another function running another application. We were using the same technique that the AES break was using of prime and probe. And then we could, from user space, be able to trigger, say, a VM exit with the CPU ID instruction. We could trigger an SMM interrupt or just an operating system callback. And we could see whether or not there was a cache impact. So CPU ID should typically not impact the cache at all unless there's a virtual hypervisor running, in which case it'll trap the VMM. The VMM will impact the cache just by executing, and then when you go back, you can kind of see that. And then my coworker who was working on the machine learning side of this was looking at using binary classifiers to be able to train what a normal-ish system looks like and then see how easily it would be to detect rootkits or other kind of suspicious behavior. Oddly enough, it's very difficult to tell between a rootkit and an antivirus system. Machine learning at the time was just not quite good enough. So take that for what you may, but for us it doesn't matter. If we see something out there that's either another rootkit or an antivirus, we kind of want to be suspicious. So you'll have two cores. One is priming the cache and then synchronizing and then waiting basically for that cache impact. The other one is calling that test function. So out 0xb2 to trigger an SMM, CPU ID for a VMM, callback or just calling a function like list directory. And then it will probe for the access pattern once that's been completed. So writing this was very complicated because we couldn't touch the cache ourselves, otherwise we'd kind of dilute or corrupt our output. But once you got it working, it was pretty reliable. And so we were able to show that you can pretty much stick it on a system, have it run, and it will tell you if there's a rootkit running in any level of, or any ring on the CPU. The nice thing was this runs in pure user space, so you don't need that much privilege. And it provides fairly granular data. So you can see, is there a VM, and then is that VM's behavior changing? So we went from that, and there's a paper out there called Conqueror, which is a way to basically use a whole bunch of randomized gadgets to both checksum to make sure you've been loaded properly, and then also to be able to establish this root of trust. So this is kind of a software Intel TXT. And so what you need is just a trusted time source and then some random seed to prevent replay attacks. And then you can see whether or not the challenge has been reverse engineered, emulated, or otherwise interfered with. So some of these gadgets I'll talk about briefly. So you want to make sure you have a CPU ID gadget, so you make sure you trigger a VM exit. And if you do this thousands of times, the time skew will actually show that there's probably a hypervisor there. Self-modifying code to detect a split TLB, which I'll talk about a little bit later. And then also you want to make sure you hook either the IVT, the interrupt vector table, or interrupt descriptor table to make sure you're not running in virtual 8086 mode. On top of that, you could also basically put this whole multi-core cache analysis inside of that to make sure it's been loaded properly. So you can use this, and we have used this to basically detect if there's kind of manual analysis, someone trying to reverse engineer that challenge binary. We can detect virtual machine presence or SMI being different than we expect. So I had to write a system management mode rootkit, and then I had to either install it or not install it, and then my coworker had to see if he could find it or not. So you can either use local hardware that's trusted, or you can do it over the network to provide the timing information. Obviously, over the network, you're going to have a little bit of kind of skew in there with latency, but it's a little bit easier than carrying around trusted hardware. And then you can use that resulting checksum to derive inference from the puffs that I'll talk about later, or extend with other things. So we kind of put this all in a thing called Secure Node. Basically, we took Conqueror and we put it into our bootloader. And our bootloader replaced all of the BIOS functionality. So it didn't rely on the BIOS at all, other than to load itself. And so what we wanted to do is we wanted to make sure that we were loaded properly and not being hooked or corrupted by that possibly malicious BIOS or pre-boot environment. We wrote it for FPGA that you can put in the PCI slot that was able to detect and act as the remote server or the trusted time device, a USB device with a microcontroller on it, kind of like an Arduino or a Teensy, or a remote server. And then there's a virtual TPM on this device that would unlock or enable that allow you to kind of approve that you are in the right modes. And so this provided software dynamic root of trust. So kind of an overview here. So the bootloader, when it's first loaded, is untrusted because it could very well have been patched when it was being loaded. It'll request a challenge, which is basically a lot of these challenges and gadgets linked together in a random order with some seeds and whatnot that are different every time to prevent the replay attack. It starts the timer as soon as the challenge is received. It runs it in this environment, and so this could be doing cache analysis. It could be doing calling IVT entries quite a bit, or setting and unsetting different IVT entries. And then once the checksum is done or the gadgets are done, then it will stop the timer and have the hardware, the trusted source, verify that. And then also within those gadgets, it's self-measuring as well to make sure both the challenge has been loaded properly and us bootloader. And so if everything is okay, now we have a trusted bootloader that we can go in and be able to do this. So I do have a demo of it, but because this was defensive software, the goal with defensive software is to not interact with the user experience at all. So it's basically just a computer booting. But I'll walk you through this kind of slowly as we oh, that's not right. All right, so what we've done in this environment is we basically put our bootloader on a USB device, and then we told it to load the host operating system, in this case Windows. And so what we've done is we've started up as a bootloader, and then we've replaced all of IVT handlers. So what the operating system would typically call back into to ask for, say, hey, load this file or print to disk, it's now calling our code. And now that it's doing that, It's finding the devices, okay. It's starting up other processors to make sure that they haven't been changed, like their IVT is not pointing somewhere else. So it starts up all the other CPUs and then puts them into a kind of a deadlock. And then it's basically doing that challenge really quickly, sending it back, and then it's going to boot the operating system successfully. But what would happen if you failed is the TPM utilities we built, which are basically software TPM, would fail to be able to unseal your VPN or attestation keys. And so that was just a quick demo of using Secure Node for a particular purpose. All right. So there are some caveats, obviously. That was pretty noticeable. Whenever you turn your computer on, you have to like do something. We were able to run this in situ, so we could drop it on a Windows system, freeze the kernel, run all of our stuff, and we had built our own USB stack so we can talk directly to the USB device or to the server, and then be able to go back from there. But there are some challenges with this in an offensive concept because a lot of the normal trusted computing requires physical presence, like provisioning a TPM or setting in a key in EFI. You don't have that ability, so that's what we're going to talk about puffs in a little bit. And also, if you alert the user, you draw attention to yourself. If you have it in a defensive concept, you can kind of, the IT guys, oh, that's fine, just ignore that error. And also, basic VM detection is not really enough anymore because Windows, Linux, basically, they all kind of come with VM hypervisors kind of running by default, like Windows 10 and Credential Guard, KVM, and then also all the cloud instances. If there is a VMM there or a hypervisor, that's not really a no-go anymore. Otherwise, if you were malware and you just saw a VM and you did nothing, you wouldn't be able to run on any Windows 10 box. So that's pretty challenging. And so the nice thing with this is that we can measure the cache impact while doing different things, like reading certain regions of memory. So if we were to, from the past talk, they were basically trapping on certain pages that were being accessed by crypto, we could access those pages and see if there was cache impact from a hypervisor trapping on those EPT instances or EPT violations. And then we would know that there was a hypervisor specifically looking at the pages that have sensitive information. And then we could change our procedures. So this is a way that you can make it more granular and get more information out of it. All right, on to puffs. So physically unclonable functions, in a nutshell, they take manufacturing variants and expose it when typically manufacturers want to hide that information. So what is manufacturing variance? Basically, as computers have gotten smaller and smaller and smaller, it's impossible to build them exactly the same. You can't have 2 chips of RAM that are exactly identical. They might be like a few atoms one way or another. And so there are always tolerances in the data sheet. Like you will do this for this much wattage or whatnot, even if a particular chip might not need quite as much power, another one might need a little bit less or whatnot. And so they have a lot of things that are toleranced. And so puffs are ways that you can use software to specifically expose those differences and get a different result on every device. So basically, you give it a challenge, and you get a device-specific or unique response. The goal would be is for these responses to be very static between running this with the same challenge. You want to get the similar response or the same response. But then if you run the same challenge and the same algorithm on a different box, and this is not just like a Mac versus a PC. This is 2 of the exact same Dells that rolled off the assembly line right next to each other. You want to get very different results. So you can tell whether or not you've been moved or offloaded or whatnot. I will caveat that puffs, physically unclonable functions, can be cloned. So before a smartass says, oh, there can be cloned, there is a paper about using a FIB, a focused ion beam, that they can actually go through and reroute chips to make them more similar to other ones. So if that is in your threat model, someone who has a very expensive FIB and lots of time and physical access, maybe this is probably not the technique for you. But at that point, they would just hire an assassin probably. All right, so why do we want puffs? Generating device-specific data is great, and we can use that as a device-specific key. So we can basically prove, yes, we're running in a trusted state and we're on this hardware. And as soon as we get offloaded to Kaspersky and they're trying to figure out what this piece of malware does, when they run it and they run that same function on their system, they're going to get a completely different response, and maybe you won't be able to decrypt your actual capability. So puffs, because they're very, very tied to the hardware, they specifically require techniques tuned for each piece of hardware or each class of hardware. New techniques are under active development. I have 2 of them that are new today. And I'll be talking later about an open source library we're going to be releasing to make it easier for other people to add new ones and collaborate on that. Another caveat with puffs is they are temperature and hardware age dependent. If you're turning your computer on in the morning and it's a little bit cold, you might get a slightly different answer because some things will expand or contract when they get warm versus if you run the same thing in the afternoon. So that's a challenge we had to overcome. So a little bit more background on some crypto stuff. Shamir secret sharing, SSS. Basically, you can take a sensitive piece of information, so a crypto key, and you can split it into n pieces, which require a quorum of n to recover the secret. And what's really nice about this, and you can think of it like really simple. Say my password is password, and I give one friend the word word, and I give the other friend the word pass. Only if they combine them together can they get my password. The problem is that I've just reduced each one of their search spaces quite drastically. And so the nice thing about Shamir secret sharing is that it doesn't do that. Even if you have m-1 pieces, you still have the same size search space as if you had 1 or 0 pieces. If you're interested in it, a great Wikipedia article, but it uses points on a high dimensional function. All right, so error correcting codes. Really briefly, there's a lot of different types of them, but they were originally kind of developed for transmission on noisy channels. You're going to increase data size to be able to add either detection or correction capabilities. And then also, depending on how much extra data you put on there, you'll get additional input. And so the real math in this is how you can add as little amount of information or data, but maximize the amount of information. So with that, we'll kind of jump into one example of a puff. So this is a scanning electron microscope of a decapped SRAM chip. And so there's a lot of cells there, which each represent kind of a bit on this RAM bank. So you'll see SRAM or IRAM. They're either on register banks or cache, or they also sometimes embedded devices. A lot of ARM devices come with IRAM themselves, which are used by sometimes graphics cards because they're much faster than DRAM. So if you look really closely, it's kind of hard to tell. They are actually like a slightly different shape in. They're all shaped the same, but if you were to like draw lines or zoom in really closely, you'd see that it'd be a couple pixels off. And that's basically is how we're going to develop this puff. And so because of that, and sometimes the sizes are bigger or smaller, when they're first powered on before they're written to, each cell tends to either be a 0 or a 1. And if you turn it off and then turn it back on again, each cell, again, tends to the same variable, to the same value. And so because of that, with SRAM, it's really, really easy. It's the easiest one to explain. Basically, you just turn on the SRAM or add it on to turn it on the power, and then you can read out a certain address. And so the challenge is basically the address and how much you want to read out. And then the response is those bit values. And so since each SRAM chip has slightly different manufacturing, giving the same challenge will provide a different output on different SRAM chips. So I talked about this already. Basically, you want to combine this with some other techniques, and so I already gave you the background on it. We're going to use error correcting code and Shamir secret sharing to be able to improve the reliability. And so what we do is we provision each puff by measuring that device in different environments to see how likely it is to change, how many bits change over time or in different temperatures. And then we can kind of get an expected failure rate or a probability of matching for each kind of device class. We then use error correcting code to correct the small errors so we can add in more or less extra data to make sure that we can match with that provisioned information. And then we can use Shamir secret sharing to both add in extra error handling by setting the M of N ratio, but also you can combine multiple puffs with different challenges or even different device hardware. So you could tie it so 2 pieces of SRAM have to be exactly the same, and if someone even switches out a different one with maybe one that they've done some hardware attack on, you won't be able to get the same result. And so that's kind of the crypto right there to make it a little bit more reliable. So puff sources, much more interesting. Trying to figure out, depending on your environment, what you have. So SRAM I already talked about, and those are common on embedded devices. All CPUs typically use SRAM for cache and for register banks. The challenge is typically you're not running early enough in the boot process to be able to use them the BIOS or the boot ROM has already gone in and changed those values. FPGAs are, I think, the original source of puffs, and they're also very common, again, on embedded devices or custom hardware. And then many of the Atom processors that Intel was making for netbooks had an FPGA also on die as well, so you could use that. NAND flash you find in a lot of places. EEPROM, and then RAM sticks, which is the one that's the most experimental that I'll talk about. So if you combine all these, you can create a really specific device fingerprint, use that as your root of trust kind of key, and that means if someone finds a very suspicious binary on their system and they ship it off to Kaspersky or Symantec to look at, you've environmentally keyed that device, that's the kind of the formal name, to a very specific piece of hardware, and then you have to ship the whole box to them if they want to do any analysis and get the same results. Sorry. So FPGAs, the way that they typically do puffs, you create two oscillators that should oscillate at the exact same frequency. But since there's slight differences in how far the different gates are away, sometimes one oscillator will beat the other one, or will come around and oscillate a little bit faster. And so you can kind of move them around physically on where you put them in the gate fabric, and then be able to kind of race them, and then the output bit stream is going to be a pretty unique stream to that region and kind of those two combinations of regions. For flash, when you program flash, you basically apply current to a cell or a block for a specified time. And so this specified time is the tolerance, basically, and you'll see that in your data sheet. However, since each cell might be slightly larger or smaller, it might take a little bit less power to actually hit that inflection point and change it. So what you do is you kind of start writing a cell, and then you cancel it before you've hit that maximum amount of time or current, and then you see if it's changed. And you do a little bit more and see if it's changed. Do a little bit more, and then you can kind of figure out, okay, this one took 3 iterations to stick. This one took 1 iteration to stick. This one took 5, and so you can kind of go through each cell and be able to develop a very specific response. EEPROMs, very similar. Basically, you program by applying current for some specified amount of time, usually like 8 milliseconds or whatnot. If you write and then kind of cancel the write too early, you will start to have errors. Those bits that have failed are because they have, again, smaller or slightly different. The nice thing with EEPROM is that every RAM stick has EEPROM on it that's exposed over this SM bus, which you can access through software. So if your target has RAM that's on like a normal DIMM, you have this available to you. Usually it's used to store timing information, so RAM overclocking software will go in and change these values, but we have access to that now. So the last one, I'm going to caveat that this one is very new, and we're still trying to figure out how good it is or if it's even reliable enough to even go down that route. Using row hammer, so real quick, I'm guessing you guys all know what row hammer is, but you read from a certain row in a DRAM, and you actually build up basically static electricity that might kind of spark out and hit a nearby row, which causes a bit flip. And so this was like the biggest, awesomest exploit ever last year, is they were able to do that and get remote code execution by flipping bits. And it was amazing. Go read it if you don't know what it is. The hypothesis we were working under and talking to some of the rowhammer developers said that this seems like it might make sense. Basically, the bits that are flipping on each row are minutely closer or more, have a little bit more connectivity between them. And so you'll define basically device and row specific pattern to flipping. And so you row hammer the same kind of regions of memory, you allocate some memory at a known physical address, you row hammer them once, and whichever bits flip, that's kind of your puff source, and then you come back later, you do the same thing again, and now you have assurances that you're on the same exact DIMMs. So I mentioned before, we're writing this all up, cleaning up the code and getting the last signatures from the corporate overlords to be able to release this. So hopefully soon it'll be up there on GitHub for anyone, but if people are really interested in this, if you hit me up on Twitter or whatever, I can probably get you some stuff earlier. But basically we're trying to make it super easy for other people to come up with new puff sources, and then basically you just drop it on any system. It'll characterize what hardware is available to it, and then be able to kind of provide puff access. So now we have a key. Now we're on to how to use it. So you can use it for a rooted trust key, so typical to the TPM remote attestation as the attestation identity key. You can use it for data at rest. So if you're trying to seal data to a specific key or to a specific device, or even you can add in by extending it in software. You could also tie it to a certain operating system version or system configuration. Or you can also use it as data in transit protection. So you could add in a PKI on top of that. And then you could have, if you have multiple implants on a network, you can make sure that you're coming from a certain device and other devices will only trust the implants that they should be talking to. So you can kind of bootstrap this to a botnet that is not going to get taken over very easily because the PKI is not there. And so basically we're using PKI, which is a real headache to set up for defenders, to be able to use that same technique to make sure that no one is trying to do a takeover of our botnet. And so the last step of the Triforce, the Zelda theme, encrypted execution. So this kind of started off as an academic research looking at how you might be able to change the instruction set. And so there are a lot of papers out there using FPGAs to simulate certain CPUs or modifications to the OpenSpark CPU architecture. It's becoming pretty popular now. So Intel, when their Skylake processors came out with the SGX secure guard extensions, which basically provides on CPU encryption and decryption. So anytime you're running anything outside of cache, it gets encrypted as it goes to memory, which is pretty cool stuff. Again, it's only in the latest Skylake processors, and it seems like they forgot to implement a very important register, so it's not a full implementation, but it's pretty exciting. And then the last year's topic was hairs, which is basically a way to do the same thing, but not with SGX. So how do we do that? Real quick background. So I mentioned split TLB earlier. TLB is a cache that basically stores translations between virtual addresses and physical addresses. If you were to look at how the paging hierarchy looks, there's a lot of lookups, and accessing memory on a system is comparatively very, very slow. So if it's already in the CPU cache, it's much, much faster. And so this is like a cache for those translations. Physically, they are separate entities. So they figured, oh, it'll be over the lifetime of the CPU, slightly faster to put the data TLB a little bit closer to the data fetch logic, and the instruction TLB a little bit closer to the instruction TLB. And so this is a picture from the Intel software developer manuals showing that there are separate instruction and data TLB. And so what you'll see is with TLB splitting, which first came out in PAX or GS Security, and then Shadow Walker and whatnot, is basically during normal operation, these TLBs are in sync, basically. If you were to read out code at a certain address, disassemble it, and then you see what it does, and actually jump to that same memory address, you're going to actually execute the code you just read. With the split TLB, you're actually moving from a parent von Neumann architecture to a Harvard architecture, and now you are basically breaking that assumption. So if you had something like PatchGuard that's making sure the kernel is okay, you actually then schedule that task that you just said is fine from PatchGuard, you were to be running something else at a different address. And so this was the Shadow Walker rootkit. Another AES extension after the AES caching attack, Intel came out with these AES and I instructions, which are basically hardware logic to do AES. They're much faster, they're more protected. They support 128 and 256-bit AES. They're very common, like you can find them in a lot of things. They provide these primitives, but they still require a lot of engineering. One cool research project was called Trezor, which stored the AES encryption keys in the debug registers on the CPU. So if you came up with a can of canned air and froze the RAM and pulled them off and put them on another system, RAM will hold its values for a few minutes, cold RAM attack. Trezor would prevent those encryption keys from being discovered. And so that was a pretty cool work. And so actually I built on top of that where I hoisted that up and I created a hypervisor that does split TLB where the AES key is stored in protected debug registers. And I transparently segregate out code and data fetches to different regions of memory. So all data fetches, including from the application itself or from an operating system, are routed to the encrypted pages. So if you were to open up a program while it's running, attach to it the debugger, and single step through it, I have a video if you want to see later of IDA freaking out. It says, you're jumping to the middle of an instruction. You're executing data because it is just seeing AES code and it thinks you're just jumping through AES encrypted data. Actually, when we first did it, we found a bug, and the error message it was trying to read out of memory was still encrypted, and it didn't have a null terminator, and so the program, while it was erroring, buffer overflowed itself, and it just popped up like a really long garbled string and then crashed. So it's pretty good preventing memory leaks. That being said, if the CPU, and this is hardware enforced, is fetching an instruction, it'll get routed transparently to the decrypted execute-only memory regions, and so the program will run basically as normal. And because we're using the TLB, it's actually pretty fast, so we're seeing around 2% performance hit. So with these capabilities, you can make it way harder for someone to reverse engineer. If you have a device-specific encryption key that is basically environmental keying to that very specific device, and you make it hard to reverse engineer on that platform, requiring it to be offloaded for analysis, you're going to make it much more difficult for introspection. You can use this to prevent detection of which puff challenges are used. So if, say, if you had that device and you knew exactly what regions of, say, SRAM you were looking at, you could turn it on and grab those SRAM values at a certain address, and then you'd be able to slowly recover that key. So if you kind of do it in a staged approach, you might be able to kind of protect that, what those challenges are a little bit better and make it much more difficult to be able to recover those puff challenges. And then you can basically create a software TPM. You can have all that kind of attestation key stored in the puffs, and then you have kind of an opaque Palladium style execution environment, and now you have basically a software TPM, and you can use all the trusted computing primitives that mostly the NSA built on top of that. So thank you, guys. You can use all the stuff I talked about, so I'll kind of skip over this pretty quickly, but yeah, you have a chain of trust, so you can measure other parts. So if you have, I can't remember the Flame malware, I believe it was, split itself up into multiple processes to make it less suspicious. So for example, all of the network I/O was run through a patched Internet Explorer process because that looks a lot less suspicious than Notepad or Word talking out to the network. So you could actually basically have measurements of all your system components and combine those in that chain of trust to make sure that your malware is intact and not being looked at. The nice thing with the hairs and SGX is that even an operating system, so if you have kernel privileges and you're trying to look down on it, and with SGX, even if you have hypervisor privileges and you're trying to look down on it, you won't be able to see what it's doing. It's kind of in that wrapped enclave. And our reverse engineering these enclaves is very, very difficult. So it helps you prevent burning those capabilities or kind of showing your hand. Obviously, this is pretty advanced stuff, so they know that it's probably not a kid in his mom's basement, but it still would help you avoid giving up the specifics. So with all of those combined, so we have the observer effect. Again, this is kind of a repeat, but ensuring that we're executing privately. We've gotten cozy in our home. We know all the kind of in and outs of all of our hardware in a very, very specific layer. And then we have the encrypted execution. So you put them all together. So this would be perhaps how you might run through an operation on a red team. So the attacker somehow delivers the initial exploit. It can characterize the environment and figure out how much introspection or if there's introspection. If there is, it might scrub the system and change tactics to go somewhere else. If not, it could establish that device key by looking around and kind of seeing what puff sources are available. It could then, once it has that, it could use typical PKI, set up a TLS where the key is device specific to rekey, kind of get the next stage of the payload or the next chunk of the malware, and then it can kind of wrap it up and execute it in an enclave. And then it can use remote attestation, the Sailor protocol, to go back to the attacker server and say, yes, I've been loaded. All components are fine. There hasn't been someone looking in at us, and that's a nice way to make sure that you're not being too closely examined. So, again, conclusion basically, when you're doing a really advanced red team exercise, you want to make sure that you're not tipping your hand. And so I think as threat intelligence goes from being a buzzword du jour, where it's just a feed of IP addresses, to something a little bit more meaningful, you really want to make sure that your tactics, techniques, and procedures and tools don't necessarily get hit up in one of those feeds, because that means anyone with a Splunk or FireEye device might catch your red team. We've shown that features present in most systems provide a lot of kind of building blocks for these trusted computing features that are usually add-ons. So a TPM or Intel TXT is a chipset addition you need to usually buy the vPro expensive CPUs for. And then you can kind of compose all this into a soft TPM and provide root of trust. I also want to make a note, this is just technology. I always make this, regardless of my talk, is offense-oriented or defense-oriented. You know, technology does not prescribe any morals, and people could say I'm a terrible person because now some bad guy is going to take this. But at the same time, you could use it for, while I use it for trusted implants, I could also now take a system that doesn't have a TPM. I could add this and add trust to some legacy device I'm being forced to run on my system. Or if I have a piece of hardware that has only maybe FPGAs on it, I can now add trust to that. Or if you're, operating in a contested network, so the NSA's IAD director, Deborah Plunkett, basically says the NSA is assuming that there are actors on our networks, and so we need to find ways to operate in a contested environment and be able to kind of create these little islands of trust to be able to operate and not lose our information and then move on to the next one. This is a way that you can kind of do that in a very dynamic fashion. I think future work into PKI for offensive networks. PKI is obviously not a very solved problem in practice, even on defensive stuff. It seems like every couple of days there's another challenge or issue. And I think it'd be really interesting to see if you add on the other things of needing stealth and persistence, what an offensive PKI network and kind of web of trust for implants and botnets would look like. And so with that, I'd like to thank you all for your time. I have a ton of references which you can get online. Are there any questions?
Do we have any questions? If you put this all together, how much time does it take to prepare, and then how much overhead do you have?
So the encrypted execution part, which is while it's actually running, is 2% or less of CPU hit. There's a little bit of startup time, but that's usually measured in fractions of seconds. If you have the puffs, so obviously it depends on what type of puff you're running. So if you're using an EEPROM or a flash puff or an SRAM puff, it's on the order of milliseconds. If you're trying to do the row hammer one and you have a RAM that's pretty resistant to row hammer or maybe completely resistant, you might have to be hammering away at those rows a really, really long time, at least to provision and find rows that are typically likely to do that. And so that would be probably one you'd establish later if you wanted to add additional assumptions. But for the other ones, if they're there, I mean, FPGA or SRAM are pretty fast. And then the software dynamic root of trust, I mean, you saw that demo, it's just, so it's quite quick. And with the timing on it, we want to make sure it doesn't go too long. If it runs too long, that's indicative that someone is trying to interact with our execution.
So we're talking seconds or less?
Except for row hammer, yeah. And I know I saw people reporting on different hardware, and some people were getting bit flips really, really fast on row hammer, just their systems, and other people were running, and I ran it on one of my new systems, and I got nothing. So that's probably the biggest variable, and that could take hours if you really wanted to, but probably not.
Any more questions?
So it's more of a defensive than offensive question.
Okay.
But that whole split TCB approach, can't we use that somehow to basically block info leaks from breaking SLR?
By doing what?
Basically, if we split data and code, like frequently they get an info leak, from a data pointer somewhere, and they use that to guess their addresses. So can't we use the split TCB to basically completely break the link between the two?
Yes. So there is a paper that cited the stuff I did called HideM, and basically did that exact thing, but they actually put really juicy looking gadgets on the data side. So when they loaded it, they're like, oh man, this has so many awesome gadgets, this is going to be perfect. But they were all kind of like honey gadgets, and so they would immediately alert. And the code was, the real code. And so yeah, you could totally use that technique. Another advantage of this Harvard architecture is, say you find like a code injection attack, like you have one kind of thing and you want to pivot to say write to another process, like the Internet Explorer. When you do that, you're going to be writing to the data page, which will never get executed. And so kind of pivoting through your system and doing that code injection attacks just don't really work. And so yeah, it's definitely useful for that.
Thank you.
Yeah.
Any other questions? All right. Thank you very much, Jacob.
Thank you.